Good afternoon. Our discussion for today is about impulse and momentum and impact. Maybe all of you are familiar with the baseball game. So the pitcher will throw the ball and the man on the base holding the bat will hit the ball. Of course, in hitting the ball, the man will exert a force and there will be contact with the ball if he was able to hit the ball. So this contact is a split seconds. So the product of the force applied by the man and the time of contact is what we call the impulse. Momentum is mass times velocity. The ball has mass and it has velocity. Even the bat has mass and depending on the applied force, it has also the velocity. So that is what we are going to discuss in this chapter. So impulse is the product of the force and time. If a force F is constant in both magnitude and direction during time t, the impulse is force times time. If the force varies in magnitude, the impulse for time dt is force times differential time dt. And the total impulse for any time t is the integral of f dt, the limit being 0 to t. The momentum of a body is the product of its mass and velocity v and is denoted by m times v. So let's go now to the relation between linear impulse and linear momentum. So that is application of impulse and momentum to rectilinear translation. From Newton's second law of motion, we have this equation 1. Acceleration is the change in velocity with respect to time. And equation 2, that from Newton's second law of motion, that force is equal to mass times acceleration. Acceleration being dv over dt. Cross multiplying, so f times dt is equals to mass times differential velocity. So integrating both sides of equation of 2. So on the right side, on the left side of the equation is integral of f dt, the limit being 0 to t. And on the right side is integral of mass times differential velocity, m being constant. So the limit from v sub o, initial velocity, to v, that is the final velocity. If mass m is constant, so the integral of f dt from time 0 to t is equals to m times b, mass times final velocity minus mass times initial velocity. So you have equation 4. You can factor out mass since mass is constant. If both m and f, mass and force, are constant, so the equation would be force times time is equals to the differential momentum. So mass times the change in velocity. The relationship derived in equation 4 and 5 may be stated as follows. Resultant linear impulse is equal to the change in linear momentum. We can write this equation in symbol. That is positive linear impulse, PLI, minus negative linear impulse, NLI, is equals to FLM, final linear momentum, minus ILM, initial linear momentum. So that is equation 6. An impulse in the same direction is the initial momentum, as the initial momentum is considered a positive impulse. Any impulse in the opposite direction is a negative impulse. Those forces opposing the motion is always negative, and those in the direction of the motion is considered positive. So let's go to the next, conservation of linear momentum. So this would be the equation. M1 B sub 1 plus M sub 2 B sub 2. These are two masses with the corresponding velocity, initial velocity B sub 1 plus B sub and B sub 2. And if these two masses are moving maybe in the same direction or in the opposite direction, so V sub 1 and V sub 2 will be the velocity before impact or before contact. And after contact, so there will be another value of velocity, V sub 1 prime and V sub 2 prime. So on the right side of the equation will be M sub 1 V sub 1 prime plus M sub 2 V sub 2 prime. So that is V sub 1 prime and V sub 2 prime are respective velocities after impact. So this would be the diagram. Two extreme cases of direct central impact. So first, the two bodies may be moving in the same direction. Maybe they have different velocities or the same velocities. And then after impact, of course, one of these should be faster, maybe W1. After impact, they will have another value of velocities. Or maybe the two bodies, for case B, are moving in the opposite direction. So you see B sub 1 and B sub 2 in the diagram. And then after impact, when they collide with each other, they may be moving in the same direction or in the opposite direction. Okay? So that is velocity after impact. So that is direct central impact. Another case is there will be oblique impact. So let's say, for example, a ball thrown to the wall or vertical surface with an inclined angle, inclined with respect to the horizontal. So after impact to the vertical surface, it will bounce back at another angle of inclination. The first angle being the angle of emergence and the other incidence, and the other is angle of emergence. Okay. So for direct central impact, if the mass centers of two bodies before collision move along the same straight line, and the shape of the body is such that the pressure each exert upon the other is also along this line, the impulse is called direct central impact. That is on the left side of the figure. Other impacts are called oblique. So you see on the second figure. So for this impact, we have what we call the coefficient of restitution. That is the ratio of relative velocity after impact divided by the relative velocity before impact. Or in symbol, that is E is B sub 2 prime minus B sub 1 prime divided by B sub 1 minus B sub 2. So E is the coefficient of restitution. So for perfectly inelastic bodies, E is equals to 0. And E is equals to 1 for perfectly elastic bodies. So meaning, the range of the value of coefficient of restitution is from 0 to 1. Other values may be in between that values. For oblique impact, the velocities in equation 8 must be the components of velocities along the common normal of the colliding bodies. So we have to consider the angle of emergence and the angle of incidence. So let's consider now the angular impulse and angular momentum. So when impulse and momentum equation is applied to rotating bodies, you see here in the diagram, so a differential mass So the force acting on it is the differential mass, or the weight of this differential mass times rho, the distance from the reference point, times omega, that is the angular velocity. And then you have here the applied force that is directed towards this. So F is the resultant force and F dt is the differential force acting on differential mass. The distance of this perpendicular distance from line of action of the force to the axis of rotation is d. So from the figure, the moment is equal to the differential force F dt times the perpendicular distance d. M is impulse moment or angular impulse. For the angular momentum, that is the integral of differential mass times rho square, the square of the distance. Or this one, this force, the differential mass times rho w times this distance. So that's why it becomes rho square. Angular velocity may be constant, so that would be outside the integration sign. So that would be integral of rho square dm. And from the last part of statics, integral of rho square dm is equal to the mass moment of inertia. dm being the mass. So mass moment of inertia, the equation would be I equals to m k squared. K is the radius of gyration, or the distance from center of the mass up to the axis of rotation. Okay, so that is equal to mass moment of inertia times angular velocity. From equation 1, force times distance is equal to I alpha, or alpha angular acceleration is equal to I times what is angular acceleration? That is differential angular velocity with respect to time. Okay. Then summation of moment at the axis of rotation is integral of f dt times d multiplied by this d is the perpendicular distance. This is differential time. Time is equal to the mass integral of mass moment of inertia times differential angular velocity. The limit is from initial angular velocity up to final angular velocity. So therefore, summation of moment at the axis of rotation is substituting the limit, that is I omega minus I omega sub O. Final and initial angular velocity. In any motion of rotation, the sum of the angular impulses of the forces acting is equal to the increase in angular momentum. So the application is somewhat similar with linear momentum. Okay, so therefore the equation can be, we have also this conservation of angular momentum, similar with conservation of linear momentum. So that is I sub 1 W sub 1 plus I sub 2, or that is omega sub 2, plus if there are another components, is equal to I sub 1 omega sub 1 prime plus I sub 2 omega sub 2 prime. I is mass moment of inertia and this omega is angular velocity. So let's have a sample problem. A 300-pound block is in contact with a level surface whose coefficient of kinetic friction is 0.10. If the block is acted upon by a horizontal force of 50 pounds, what time will elapse before the block reaches a velocity of 48.3 feet per second, starting from rest? If the 50-pound force is removed, how much longer will the block continue to move? So this is the diagram. a 300-pound block resting on a horizontal surface. So the mass is 300 pounds, the applied force is 50 pounds. There is friction between the block and the horizontal surface. Since P is directed to the right, so the motion will be directed to the right. So force of friction would be directed to the left. So the force that we have to consider in the equation is the force parallel to the direction of motion. So let's solve. Summation of forces along x being in the direction of motion equals to 0. Or simply the impulse momentum equation. That is, impulse is force times time. What is the net force acting on the body? That is the applied force 50 minus the frictional force. What is the frictional force? That is equal to coefficient of friction times the normal reaction. The normal reaction is equal to the weight of the block. So net force times time is equal to W over G. Mass, it should be mass. So that is weight over G. W over G times the velocity. It starts from rest. So initial velocity is 0. So we use only the final velocity, 48.3 feet per second. So from this equation, you can solve for time. So time is 22.5 seconds. What is the question? If the block is acted upon by horizontal force of 50 pounds, what time will elapse before the block reaches a velocity of 48.3 feet per second starting from rest? So by applying 50-pound force, so after 22.5 seconds, so the velocity of the body is 48.3 feet per second. So it starts from rest. The next question is, how much longer will the block continue to move? So the body is already in motion. Definitely, even if you remove the 50-pound force, still it will continue the motion up for some time. So how much is that? So the body has already 48.3 feet per second. So after attaining this velocity, you remove the force. So what will happen? So what is now the only force acting on the body? That is the frictional force. So that frictional force is times time is equals to mass W over G times velocity. So the time is 15 seconds. So meaning, after attaining 48.3 feet per second velocity, and then removing the force, it will continue this rectilinear motion until up to 15 seconds. And after that time, the block will stop the motion. Let's go to the next problem. A force of 300 pounds pushes a 200-pound block up an inclined plane whose slope is 3 vertical to 4 horizontal. So it's a 3, 4, 5 triangle. If the coefficient of kinetic friction is 0.2, determine the time required to increase the velocity of the block from 10 to 50 feet per second. So this time, initial velocity is not equal to 0. So this is the diagram. The weight of the block is 200 pounds. So the inclination is 3 vertical, 4 horizontal. So the hypotenuse would be 5. So we rotate the axis. This would y-axis normal to the inclined surface, and let x-axis be parallel to the inclined. So this weight will have components along y-axis and component parallel to the x-axis. So the normal reaction here is equal to the y component of the weight. And the x component is equal to 200 times 3 over 5. The frictional force is equal to Normal reaction times coefficient of kinetic friction. So let's apply now impulse momentum equation. What is the positive impulse? The positive impulse will be caused by the 300 pounds. The force against the motion is the the x component of the weight, 200 times 3 over 5. And the normal reaction is equal to 200 times 4 over 5. Multiplied by the coefficient of friction, this is now the force of friction. And then this net force multiplied by time is equal to mass W over G times final velocity minus initial velocity. Simplifying the equation and solving for time, so that would be, the time would be 1.68 seconds. So the velocity will change from 10 feet per second to 50 feet per second. Let's go to the next problem. A body is thrown vertically upward with an initial velocity of 9 meters per second. Assuming that it falls freely after it comes to rest at the top of its path, find its velocity 2.5 seconds after discharge. So say for example this, a ball thrown vertically up, initial velocity v sub o, final velocity that is given 9 meters per second. We don't know the final velocity, but there is a given time, 2.5 seconds after discharge. So we can solve this in two ways. First, by impulse momentum equation. That is, force times time is equals to mass times final velocity minus mass times initial velocity. What is the force? There's no given force that is applied here, only velocity. So the force that is against the motion is the weight of the body. So the weight, it's negative because it's against the motion, vertical motion of the upward motion of the ball. So the weight times 2.5, the time, is equals to mass, W over G, times velocity, minus W over G times 9 meter per second. Okay, solving, you can eliminate W. So you can solve for this time, this final velocity. So negative 2.5 G is equals to V minus 9. And V is equals to 9 minus 2.5 times 9.81. So therefore, velocity is negative 15.525 meter per second. So why the velocity is negative? Is there negative velocity? Okay. Definitely there's no negative velocity. That it only means that the ball is already on its way going back to the earth. Okay. So going down. Okay. With the same problem, so there is another solution. Let's consider the body as freely falling bodies in rectilinear motion. So what is the equation? Final velocity is initial velocity plus acceleration times time. What is the acceleration? That is the acceleration due to gravity. And since it is going up, G is negative. So substitute the given values to this equation. So V is 9 plus negative G times time. And you will get this value. So V is negative 15.525 meter per second. So we get the same answer considering freely falling bodies and impulse momentum equation. So that's why I'm telling you that work energy method and impulse momentum equation is just a method that will be applied to the first four topics that we discussed. Rectilinear motion. Of course, the first one is introduction. The second one is rectilinear motion. The third one is curvilinear motion. And the last one will be the rotation. So it's just another method. Okay, now let's discuss example 4. Determine the velocity of body B in the figure after moving 5 seconds starting from rest and starting with a downward velocity of 6 feet per second. So this is the diagram. It is similar to the problem we solved in chapter 2. Only in that problem, we are solving for acceleration. We also solved this problem in chapter 5. However, the mass of A and B are interchanged. A is 300 pounds and B is 200 pounds. Okay, so for system of pulleys, frictionless pulley. So in analyzing this, we consider the internal forces. So we draw the free body diagram of A. For cord passing over frictionless pulley, there is one value of tension only. Then free body diagram of the pulley. Then free body diagram. This is another cord, so T sub B. And free body diagram of block B. Okay. So assuming A will move upward and B will move downward. So T sub A will produce positive impulse and the weight is negative impulse. So T sub B, this will move downward, block B. So the weight will produce positive impulse and the tension will produce negative impulse. So from this free body diagram, we got T sub A is twice the tension at B. So in that case, velocity of A is only 1/2 of B sub B. If T sub A is 3 times tension of B, so B sub A is 1/3 of velocity of B. Okay, so that is the relation for velocity and tension as well as the acceleration. In that case, acceleration is also 1/2 of the acceleration of B. Acceleration of A is 1/2 of acceleration of B. Now, let's apply impulse momentum equation. There's a correction with the one I gave you, the first PDF. So, it should be B minus B sub O. The one I gave to you is B squared minus B sub O squared. That is for kinetic energy. Okay, so applying the given for first for block A, so T sub A minus the weight times time is equals to the mass, which is W over G times B sub A minus 0. Initial velocity is 0 because it starts from rest. So substitute T sub A is 2T sub B minus the weight times time is mass, weight over acceleration due to gravity times B sub B is B sub A is 1/2 B sub B minus 0. Simplifying, we have equation 1. Applying to the impulse momentum equation to block B. So 300 will cause positive impulse and the tension in is negative impulse times time equals to mass W over G times the velocity. Simplifying, we have equation 2. And solving equation 1 and 2 simultaneously, or you equate the two equations, will give you B sub B equals to 92 feet per second. So moving on, with the initial velocity equal to 0, so we will be using the same free body diagram and the same equation. Only this time, initial velocity, let's say that is for block B, is since B is required 6 feet per second. So for initial velocity of block A, it would be half of that, and that is 3. So substituting all the given value to the impulse momentum equation, we will have equation 3 and 4. And equating the two equations, we will get velocity of B to be 98 feet per second. Let's go to the next example. A 500 Newton body initially at rest is acted upon for 9 seconds by a variable force F equals to 100 square root of T. And by a variable resisting force F sub 1 equals to 30 minus T during that time. What is its velocity at the end of 9 seconds? So let us assume that the positive force producing impulse is directed to the right. So the resisting force should be in the opposite direction. So this would be the diagram. So solution, applying impulse momentum equation for variable forces, that is, the positive impulse F dt integrating limit is 0 to 9 seconds minus the negative impulse, the resistance F sub 1 dt, the limit 0 to 9 is equals to the change in momentum. F is 100 square root of T, so 100 T raised to 1 half dt. The limit is 0 to 9 minus integral of F sub 1, 30 minus T times dt. Limit 0 to 9 is equals to 500, the weight over g, times this velocity. Initial velocity is 0 because it starts from rest. Integrating the left sides and simplifying the equation on the right side. So substituting the limit, we can get the velocity equals to 38.1 meter per second. So that is the velocity after 9 seconds, and it starts from rest. Okay, let's discuss the next problem. A ball is thrown at an angle theta against a smooth floor as shown in the figure. Okay, where's the figure? So this one. It rebounds at an angle of P prime or theta prime with the floor. Show that the coefficient of restitution is given by the expression E is equal to tangent theta prime over tangent theta. So what we are going to do here is to, since that is inclined oblique impact, so we do the triangle. So this is velocity of before impact on the floor. So it will have vertical and horizontal component. This angle is theta. Let's say this is, I forgot the letter here, it's point O. So you have triangle AOB. And then another triangle, this is velocity after impact. It will have its horizontal and vertical component. The angle of emergence after the impact is theta prime. So triangle COD. So this point of contact here is point O. So solution in triangle AOB. B sub x is B sub y cotangent of theta. Okay. And B sub prime in triangle OCD is B sub prime x is equals to B sub prime y cotangent of theta prime. Since the floor is smooth, so B sub prime x is equals to B sub x. Hence, B sub x is B sub prime y cotangent of theta prime. Okay. So we equate these two are equal. So B sub x prime is B sub y prime cotangent theta prime. And from here, since they are equal, we can also write B sub x is B sub prime y cotangent theta prime. We equate equation 1 and 2. So what will happen? So when we equate, we can write B sub prime y is B sub y cotangent theta over cotangent theta prime. E is velocity after impact divided by velocity before impact. It's a single body. There is no two colliding bodies. Only one. It's colliding with a fixed floor. So definitely the floor will not move. So what we are going to consider only is the velocity of the vertical component of the velocity after impact divided by the vertical component of the velocity before impact. It should be the same direction. Initially, we equate the velocity in the horizontal direction. And then, for coefficient of restitution, we equate, okay, it's vertical velocity, component of velocity after impact divided by the vertical component of velocity before impact. So what is B sub y prime? B sub y prime is B sub y cotangent theta over cotangent theta prime divided by B sub y. So we can cancel B sub y. If we bring down cotangent theta is 1 over tangent theta. And 1 over cotangent theta prime is tangent theta prime. So therefore, for oblique impact, the coefficient of restitution is equal to tangent of the angle after impact divided by tangent of the angle before impact. That is the answer. Next. In the figure, let's show the figure. The cylinder A weighs 450 Newton and has a radius of gyration of 165 mm. If the system starts from rest and no slipping occurs, determine the linear velocity of the system and the tension in the cord at the end of 2 seconds. So this is a cylinder. The radius is 0.2 meter, cylinder A. Then there is a cord attached to it, so the velocity is directed to the right. Definitely block B, 180 Newton, will move downward. There's no given coefficient of friction, so we assume this is a frictionless pulley. So there's no slipping. Okay, there is the normal force here. The weight of this is 450 Newton. Okay, 450 Newton. Okay. And then, so there is rotation in this direction. The angular, what is this? The angular impulse, the momentum, I of omega here in this direction is I in this direction. Okay, then you have here mass times velocity. This is tension caused by the cord times time. So all of this, so times time. Impulse, 450 times time. The tension times time. Okay, mass times velocity. And then you have here frictional force times time. This is the normal reaction here. The normal reaction, of course, is equals to the weight 450. This is 180 Newton. This is this one times time. Okay. In figure B, so this portion, although this portion is cut, so this is 450 times time. This is 180 times time. The wheel is taken as free body with the reverse linear and angular moments applied to it. So it will be in equilibrium. I sub C, okay, so this one is W over G K squared. So the weight 450 over 9.81, this is Newton, so we use 9.81 times K, 165 mm, that is 0.165 meter square. So that is the mass moment of inertia. Summation of forces horizontal equals to 0. Okay, so here, the tension times time minus force of friction times time minus mass times velocity, or you can put it on the right side equals to mass times velocity. Substituting the time, so this would be the equation. Simplifying the equation, we have tension equals to F plus 2,500 over 109 times velocity. Now, for the moment, so the friction times the radius times time. So this one, the moment about the center, is equal to the mass moment of inertia. We compute that equal to 1.25 times angular velocity. Substituting the given force, frictional force times time times the radius is equal to I sub c is 1.25. What is the relation between linear and angular velocity? Linear velocity is angular velocity times the radius. Or angular velocity is linear velocity divided by the radius. So v over 0.20. Simplifying the equation, we have F equals 15.625 B. For block B as a free body diagram. So the tension in the cord, there's only one tension here, times time, plus mass times velocity is minus 180. The weight is against the motion. Okay, 180T equals to 0. Okay, or you can write here 180T minus tension times time is equal to mass times velocity. So that is the same equation. So we just write here summation of forces vertical equals to 0. Or you can write impulse is equal to change in momentum. So 180 times t positive, this is because it's going down, minus tension times t equals mass times velocity. So the result would be the same. Substituting the given time and the weight or mass 180 over g. Simplifying, we have this equation 3. So we have equation 1. We have three variables, t, f, and v. This is f and v, and t and v. We can substitute equation 2 to equation 1. And then solve the equation simultaneously. Okay. And then it will give you the velocity, 3.771 meter per second, and the tension in the cord, 145.405 Newton. So let's consider example 6.9. The initial velocity of the block in the figure is 20 feet per second downward. So let's show the figure. The coefficient of kinetic friction at the brake is 0.25. The centroidal mass moment of inertia of the drum, so this one, is 10 foot-pounds second square. So it's the same as unit raised to 4. But since this is mass moment of inertia, so that is foot-pound second square. Find the time required for the system to come to rest after the brake is applied. So this is the brake. So if there is a weight attached to it, definitely it will rotate in clockwise direction. This block is moving downward. But when the brake is applied, you applied force P here, it will stop. Okay. So first, let us consider the brake lever. So we take summation, assuming there is no only the free body diagram of the brake lever. So there will be normal reaction at the point of contact. There is a given coefficient of friction. Okay, summation of moment at A equals to 0. So that is P times 4 minus the normal reaction with respect to the brake is directed upward, N times 1. So the normal reaction is 400. Force of friction is Fk times N or mu K. Coefficient of friction times normal reaction. So 0.25 of 400. So force of friction is 100 pounds. Applying impulse momentum equation, we consider all the moments, summation of moment, that is the net force times time times the radius. So this force, it will produce clockwise moment, 100 times the radius 2 times time, minus the frictional force, it's in the opposite direction, 100 times the radius 4 times time, is equal to, so on the right side, this is the change in momentum. So W over G, 100 over 32.2. Initial, final velocity is 0 because it will come to rest. Minus initial velocity is 20. Times the radius. Okay, because we are solving for moment. This, okay, equals, plus. The mass moment of inertia is given 10 foot-pound second square times the difference in angular velocity. The velocity is 20, the linear velocity. So divided by the radius, which is 2 for this one. So that is the angular velocity, 10. So the final is also 0, minus 10. Solving for time, the time is 1.121 seconds. So it is rotating. When you apply this force speed, there is a contact with the brake lever. It will stop after 1.121 seconds. Okay, let's consider this problem. I think this would be the last problem. The balls A and B in the figure are attached to the stiff rods of negligible weight. Initially, the ball B is in vertical position and A is in this position, 60 degrees from the vertical. Ball A is released from rest and allowed to strike at B. So it's released from this position, then it strike at B. B is initially at rest. Then definitely when it strike, it will rotate in this direction. If the coefficient of restitution is 0.5, determine the angle theta through which the ball B will swing. If the impact lasts for 0.01 second, also find the average impact force. Okay. So from this, we can form a right triangle. So 60 degrees. Let's say this distance is h. So this distance up to center of the ball is b. Also on the right side, so this one. So we do right triangle. This height is h. And this distance up to center of the ball is c. The total length of the cord here is 10 feet. The other one is 8 feet. So considering the first triangle, cosine 60 is h over 10. So you can solve for h is 5 feet. So therefore b is 10 minus 5 is also 5 feet. So we have this formula for equation. Velocity is the square root of 2gh. Considering the vertical distance. So that is 17. It is released from rest. So initial velocity is 0. So we have only this equation for velocity. 17.944 feet per second. So using conservation of linear momentum. So we have only ball A which started the motion. B is at rest. So we have WA, B sub A is equals to, when it reaches this position, the ball A, it will impact ball B. Then it will move. So on the right side, WA, B sub A prime plus WB, B sub B prime. Substituting the given 30 times the velocity is equals to 30 B sub A prime plus 20 B sub B prime. Simplifying, we have this equation 1. Then using coefficient of restitution, B sub B prime minus B sub A prime all over B sub A minus B sub B. Substituting the given value, then we have equation 2. So solving equation 1 and 2 simultaneously will give you the value of velocity of A after impact or at the point of impact contact 6.45982 feet per second, and the velocity of B to be 17.22682 feet per second. Also, B sub B prime is square root of 2gc. See this height. Okay. So, substituting the equation, you can solve for C. From the figure, h is 8 minus c. Okay. So, therefore, h is 8 minus 4.6081. So, this is 3.3919 feet. The height that you have to consider, initially that is the position, then it moved from here. The height that you have to consider is this one. On the other side, the height that you have to consider for velocity square root of 2gh is b. It's just happened that h is equals to b, 5 feet. Okay? So, you know h. You know this is 8. So, you can solve for cosine theta. That is adjacent side 3h, 3.3919 over hypotenuse 8. Therefore, theta is 64.9134 degrees. Okay, so that's all for impulse, momentum, and impact. Thank you for listening.